Yeah, can you all hear me and see my screen?
Yes, sir.
Yeah, so good morning, everyone. Sorry for the slight delay. So yesterday we were doing the random module. We got an introduction to that. And I hope you had a chance to practice the functions in the random module. Today we will extend our practice with the random module. We try to create some classes that use functions in the random module. Okay, we'll do some exercises like that. Okay, so I had also answered all the queries on the assessment 3. I don't think there are any more outstanding questions. So there were a couple of clarifications to be made and adjustments I will make in these course. But if there are any other questions that anyone has, I think we have gone over it pretty well. But if there are any other questions that still remain, please post it in the classroom and we'll address it. Okay. So any questions from yesterday's session on the random module? Anyone? So we used some functions in the random module and created a list of random numbers. We combined comprehensions and functions in the random library. And using these comprehensions, we were able to create a series of random numbers. So we have a few tools we can use now, and we are able to address some larger problems. Okay. Now, one of the things we were trying to do yesterday is work with the. So let me first import the random module. So all of you, please import. One of the things we were trying to work with yesterday was the random.choices. Okay, and it seems that the random.choices has been updated for Python 3.9, and in 3.85 the syntax is a little bit different. So you see some of these functions in Python are still evolving and they change from one version to the next. That is why it is better to have the latest version. And then when you go to the official Python documentation at docs.python.org, you'll find always the latest documentation for the latest version of Python. So it's better to have the latest version of Python installed because some of these functions are still evolving. Now, in order to get to do sampling without replacement, we saw the sample function. Okay, so let's again create our lists to work with this. So let's say I have a list like this. Okay. And let's say I want to sample from this list. So what I say is random.sample of LSD, and I give the size of the sample that I want. I want a sample of size 5, a random sample of size 5. And I do this and I get this. Now, so what we can do is we can also assign some, we can also try to do some sampling with replacement. Okay. So when we want to do sampling with replacement, the method we can use is random.choices. But there is some syntax here in the population LST, and k is equal to 5. And let's see what happens. So now I get it. Okay. So I have to give a named argument for k. And now what I have is a sampling with replacement. And you see, in fact, the 1 is repeated 2 times. So every time you sample from the population, after that, you replace the element back in the population. So the next time we are trying to sample, we have the full population available to us. So this is known as sampling with replacement. So Python, let's say this random module lets us do both sampling without replacement and sampling with replacement. When we want to just get one random element from the sequence, we just say random.choice and just give the name of the sequence, the variable name, and we get one random element, that is 2 here. If we want to sample a size, a certain size, then we have an option to do the sampling either with replacement or without replacement. So all of us who are familiar with statistics would know this. For example, when we are doing bootstrapping of a sample, okay, some of you might know about bootstrapping, a statistical procedure, where we're essentially resampling from the sample. Can anyone tell me bootstrapping involves sampling with replacement or sampling without replacement? Bootstrapping is sampling with replacement or without replacement? Anyone? Anyone has done bootstrapping here? Yes, no?
No, sir. No, sir.
No, okay. All right, okay, fine. Okay, so this bootstrapping is used when the population, we can only take one sample from the population, but we want to find the variability of an estimate from the sample. Then what we have to do is basically bootstrap the sample itself. We have to resample the sample many times. Now, when we do that, already we have only a sample, and if you resample without replacement, essentially you will end up with the same sample if you want the same size. Now, but if you sample with replacement, so every time you take an element and then you put it back, then the bootstrapped sample will be different from the original sample. Okay, so in that way we have to do the bootstrapping with replacement. So when we want to do such a thing, we have to use random dot choices. Okay, and when we are sampling without replacement, it is random dot sample. Only when we have the original population and we want a random sample from the population, we do random dot sample. When we are resampling from the sample, for example, during bootstrapping, we have to use random dot choices. Okay, so these are two applications of these methods, of these functions. So they are very straightforward functions, but these are some applications. Now, a classic probability problem is where you have urn or a container where it has balls of two different colors. Let's say red balls and blue balls. So let's say my urn is equal to red and blue. Now, from this urn, you're supposed to take a ball at random, and then we want to find the probability that it is a red ball or something like that. Okay, so usually there are 5 red balls and 10 blue balls, or some counts like that. So when we want to do this, okay, so what we can do is we have to assign some counts to each of these elements. Each element is repeated so many different times, and then we want to sample from that. So in order to do that, what we can say is random dot sample of one, and we can say there is a let's just see what that argument is. There is a count argument. Okay, there's no count argument here, but I think in the random dot choices we have a count. Random dot choices. Okay, so there are some weights. So let's use these weights. So okay, so you see the weights are not specified. The selections are made with equal probability. That is the default. Now what we will do is we'll specify some weights. Okay, and it's from the on. My weights are red ball. Let's say there are 8 red balls for every 2 black balls. So the weight is 0.8 and 0.2. And then let's say okay, I want to sample 10 times from here. So when I sample 10 times from the zone, I must on average get 8 red balls, 2 blue balls. So let's see what happens here. You see, in fact, we have a greater abundance of red balls over the blue balls. In fact, we get exactly 8 red balls and 2 blue balls. It need not be like this, okay? But this time it has happened like this because we have given the weight. Let's do it again and see again if we get 8 red balls and 2 blue balls. So now you see we have a blue here, we have a blue here, and one more blue here. So we have 3 blues and 7 reds. So even though the weights are like this, it's still a probabilistic sampling, isn't it? So there is a chance that you may get 3 blue balls. There's even a chance that you may get 10 blue balls, but the probability is very, very low. There's a good chance you may get 10 red balls. Okay, and the probability is like not very low. It is more likely than getting 10 blue balls, isn't it? All right, so that's to do with probability. We can actually exactly calculate the probability for each of these observations. All right, so I'm sure you're doing a paper on probability and statistics, and it's easy to calculate these probabilities. All right, so we can specify the weights like this and also execute the choices. Now let me pose a question. Now suppose I want to do sampling with replacement from a certain list. from a certain sequence. Let's keep it general. So I want to do sampling with replacement from a certain sequence. I might very well use random dot choices. Now let's say that I'm not permitted to use random dot choices. Okay, I can use any other function within random. Okay, only thing is I should not use random dot choices. Okay, so let's say I have an older version of Python where the random dot choices does not run. Okay, now in that case, anyone has any idea how I can do the sampling with replacement from the sequence? Is there any other way to do it? Anyone? Let me pose the question here. So, how to sample with replacement? Okay, but without using random dot choices. Okay, that's the question. So how to sample with replacement but without using random dot choices? Anyone? Any idea? So there's a particular function we've already seen that can be used. Okay. Yeah, Keshav has given a answer, random dot choice. Excellent. We use a list comprehension for this. Okay. And we combine that with the random choice. Okay, so every time each element is generated randomly by using random dot choice. And this is essentially similar to the comprehension constructions we saw yesterday. So I can just say random dot choice of earn or LST or xn range of, isn't it? So we are now familiar with this construction for xn range of n. For every iteration, what I want to do is randomly sample from the sequence and get one element. For that, the function is already available. That is random dot choice. So we just do this over and over again in a form, and we have a list comprehension out of it. So again, we have a sort of a sampling with replacement. 2 is repeated many times here, isn't it? In fact, the 2 is repeated 3 times. 4 is repeated 2 times. 5 is repeated 2 times. So basically, we are sampling with replacement. If you see the list, it is just 1, 2, 3, 4, 5, 6, 7, 8. All right. So you see, this is essentially doing what the random dot choices is also doing, except that explicitly we are doing a list comprehension here. Okay, but the random dot choices will be much faster in terms of implementation. So if you have a large population and you want to randomly sample from the large population, it's better to use random dot choices. Okay, the list comprehension will slow you down. Okay, all right. So apart from this, we also saw about random dot shuffle for computation of a given sequence. And we also saw how we can permute a immutable sequence in place, not in place, but by reassignment, isn't it? Okay, we saw a method to do that yesterday. Okay, using some tricks in Python. All right. Now, we've also seen the different distributions that the random library makes available to us, and how we can generate random deviates from any of this distribution. For example, if I want to generate some 10 random deviates from the uniform distribution between 0 and 10, all I have to do is say random dot uniform. Okay, so the uniform function is the one that pertains to the uniform distribution. It takes 2 parameters. What is the left end and the right end? So 0, 10, both inclusive. For xn range of how many ever random deviates I want. I want 10 random deviates. All right. So now you see I have from stuff like this. Now suppose I want to only have integers from 0 to 10, random integers. Okay. Okay. So then I can slightly modify this and say I can say we can multiply this. You can see the number of floats here. okay, and multiply it and do a int of that, and then we'll have a sort of a. It won't be perfectly random because when we are doing the int, some information is being lost. All right, so. If you really want to have some integers between a certain sequence, we have to use the function random that we've already seen. And let's say we want integers between 0 and 100. And now we can get the integers in this manner. Okay, so all sorts of things can be done. And we have some really fancy distributions that we can access from the random library, including the beta variate, the gamma distribution, exponential distribution, the normal distribution, and other distributions like Weibull, von Mises, and also the Pareto distribution. Okay, so all these are available to us. Okay, now let's take up a small exercise here. Okay, and where we combine some objects with this random module. Okay, so what I want to do now is basically simulate the coin flipping experiment. Okay, so let's say we have a coin, and when we flip the coin, there are two outcomes. Okay, so what are these two outcomes?
Heads or tails?
Okay, head or tails. Now, what is the probability that I'll get a head?
1/2.
0.5?
Yes, sir.
Is it always 0.5?
Yes, sir.
If the coin is unbiased.
Does it depend on any other factor?
If the coin is unbiased.
If the coin is unbiased. Okay, so now there is a catch. Do you know of any biased coins?
Sir, like both the sides can be heads or both the sides can be tails, like that, biased. Or a fake coin which has
Okay,
both
that's a
of them.
different sort of. Yeah, so that's a different sort of bias that we see in the film or movie. Okay, where in the end it is revealed that the coin always turns up heads. No, there the probability is always one. There's no chance that we'll get a tail. Okay, so that's a different sort of bias. Let's say a filmy bias. Okay, we're not talking about that sort of a bias. It is also possible. But that is outright, sort of a bias. But there are other ways to bias a coin. Can anyone think of any other ways? So there are ways to bias a coin so that the probability is not exactly 0.5. The probability is like, more than 0.5 or less than 0.5. Okay, usually the heads will be more than 0.5. Now, why that is the case is because, we can sort of make the coin heavier. We can make the coin heavier on the head side. Okay, so the head side is where we have something being embossed, isn't it? Okay, and there if we make it heavier, it's not really hard. Okay, and this is a recurrent problem, because coin flipping is a very common practice to sort of say who is going to bat first or field first and all these things, isn't it? Okay, but what we can do is that the coin can be biased in this manner by making one of the sides heavier, usually the head side. Now you can make it heavier by using a different metal or adding more metal, whatever it is. Okay. Now when you do that, if the head side is heavier, okay, then it's more likely that it will land on the heads. Okay, so that is a simple physics. Okay, so if you make the head side heavier, it makes it more likely it will land on the heads. Okay, so all right, so that is the essentially how we can bias the coin, and it's not something that is unknown. It happens all the time. Okay, it happens all the time. All right, so let's say you go to one of these places where a coin is tossed, and then you make your winnings or something like that, isn't it? Okay, so again, we find that, is it a fair coin or not? Is it an unbiased coin or not? Okay, and this question is always there because it is not hard to bias a coin. So this factor, okay, that tells us whether it is equally likely, whether we get heads or tails, is known as the fairness of a coin or bias of a coin. More properly, technically, it's called as the bias of a coin. Okay. And if the bias is 0.5, that means it is equally likely heads will come up or tails will come up. If the bias is not equal to 0.5, then the coin is actually biased. Okay, if bias is 0.5, the coin is unbiased. Otherwise, the coin is biased. All right. Now let's create a object, coin object, and which can be flipped. There's a method for flipping the coin object. Now, when we flip the coin object, there has to be an outcome, and the outcome is a random outcome. Okay, it has to be like a actual flipping we do in real life. So in order to get a random outcome, basically we have to use a function from the random library. Okay, so we can simulate coin flipping. Okay, so it's easy to simulate, and we can find out if you flip the coin 1,000 times, how many heads you will get. Okay, so and then it's sort of it's then from the distribution of heads and tails, there are a few things we can study. Okay, or we just want to get a random sequence of heads and tails from a coin with a certain bias. So you give the bias as a variable to the coin object, and then you call the flip 1,000 times, and you record the outcome of each of these experiments. Now you have simulated coin flipping experiment. Okay, it's a very simple experiment. All right, so now what we will do is we will implement a class for a coin object that has includes the bias of the coin as a instance variable, and which has a method for flipping the coin. Now outside of this, we create a function that flips the coin a user specified number of times and returns the sequence of heads and tails. Now, is the problem clear to everyone? So let's do this. Let's do some scripting. So what we will do is, okay, coin class bias is an instance variable. Okay, so the bias is what I've discussed thus far. Okay, and then there's a method. What are the methods we want? Flip. Okay, to flip the coin once and return the outcome. Now, what is the outcome here? Heads or tails. Okay, so this is the class we want to create. So how do we create this class? So we say class coin. It does not inherit from anything, so it's just of the object, and we do a constructor init and self comma bias. The bias, if it's not specified, we take it to be the default value. That is, the coin is unbiased. So the default value is equal to what?
0.5, sir.
Good. So it's equal to 0.5. Bias is equal to 0.5, unless we want to specify a different bias. Okay. And so now we say self.bias is equal to bias. So now the coin object, this is the constructor. This is all we need in the constructor. So now what we want to do is we want to create a method called flip. And we're only going to flip the coin itself, so flip of self. Okay, can anyone tell me what needs to go in here?
So the function should start with a def keyword.
Yeah, here it's just the method. We want a method for the coin object. But after we create the coin class, we want to create a function that will flip the coin 100 times or whatever times. But this flip is just flipping the coin once, and it's a method of the coin object. So the method is just flip, and it flips the coin once and returns the outcome. But outside, we'll write a function to simulate coin flipping 1,000 times. Okay. So basically, given a coin object, I would like to flip the coin. See, even if I want to flip it 100 times, I have to start with one flip. The same flip, I do it again and again. Okay, so first there must be a method to flip the coin once. Okay. Is that fine? Can anyone tell me what should come in here? What is the code for the flip method?
So a random dot choice of self.
Random dot choice of
Self.
self. How can it be self? Self has only one instance variable. Self is the object. It's not a sequence.
Okay.
Anyone? So let's import the random here. How will I flip the coin once? Let's say it's a biased coin. And the bias of the coin is given by bias, self.bias. Based on this, anyone?
Sir, it will choose.
See, the coin is just a, yeah, go ahead.
It will choose randomly either head or tail based on weight of 0.5.
Correct. How will it choose randomly from head and tail?
We can use a list containing head and tail, sir, and then we can write it as that list dot that is random dot choices of that list comma weight of 0.5.
Good, excellent. All right, so I was just looking for random the choice of list. Yeah. So you just create a list that contains heads and tails. Okay, and we choose randomly from the list. That's all. Okay. So this head and tail is not explicitly a part of the coin object. The only thing that is part of the coin object is the bias. Okay, but the head and tail is a class variable, isn't it? It's a class information, and we can directly use it. So we can say outcomes, possible outcomes is equal to head or tail. Okay. And now what we say is we can say random dot choices. Since we want to use the bias, we have to specify the bias as a weight. So random dot choices of outcomes, and we want only one flipping. So k is equal to 1, but weights is equal to bias comma what? Who can tell me what is the other element in the weights?
1 minus self dot bias.
1 minus self dot bias. Excellent. Okay. Excellent. So it's actually self dot bias and 1 minus self dot bias. Because we are only passing the self object here, the bias is just local to this constructor. So the only variable we have access to is the instance variable, and that is the self dot bias. And it's self dot bias and 1 minus self dot bias, random choices, and I want only one outcome, so it's k equal to 1, and we need to return this. Now I could have used random dot choice, okay, and I just say outcomes, but the problem here is that it assumes the coin is unbiased. Since I want to factor the bias of the coin, we use random dot choices, but the k remains 1. Okay, so let me just remark that here, and I will say random dot choice of outcomes assumes coin is unbiased. Okay, if that is the case, we can use random dot choice. Otherwise, we have to say return random dot choices of this. Okay, now with this our coin object is done. Now let's proceed to writing the function. And what is the function? I want to simulate the coin tossing experiment a certain number of times. How many times? 100 times, 500 times, 1000 times. So this number of times is given by the user. So we can write a function for this which takes the n as the input from the user. And for this n, I want to simulate the coin tossing experiment n times. And what is the outcome of this? I want to return a sequence of heads and tails that were produced by this simulation experiment. What is the sequence of heads and tails? Okay. Okay. So let's say def coin simulation. Okay. And it takes number of trials as the okay, let's say of n, and we'll provide some sort of documentation doc string for that, and we'll say n is the number of trials, returns the sequence of heads and tails as from the simulation experiment. Okay. All right. So this is our coin simulation. Okay. Now first we must instantiate a coin object. In order to flip a coin, I must have a coin object. So how can I instantiate a coin object? Now there's another thing, coin simulation, there must also be the bias. Okay. So let's say bias is the bias indicates the bias of the coin. Okay. And n is the number of trials. And returns the sequence of heads and tails from the simulation experiment. All right. Okay. So now I have to instantiate a coin object with the given bias. How will I do that? How can I create a coin object with the given bias?
Coin space, object name, and the brackets bias, sir.
Oh, that's not Python. That's a different language. How can I create a coin object in Python? Yours sounds like Java or something. I don't know who said that. It's very simple to create objects. Once we have defined the class, how do you object, class object?
Object name equal to coin and the bias value in the brackets.
Okay, so we just say coin of bias and we assign this to some object name. That is it. Let's say the object name is small c coin. Coin is equal to coin of bias. So coin is my coin class. Okay, and the coin class is here. And we are giving a actual bias that is from the function. So we are specifying the bias here. All right. So now my coin object has a bias. If I want to print the bias, I just say print of coin.bias. Let's say I want to know whether my coin is biased or not. So I can say if bias coin.bias, let's say, is equal to coin phi print coin is unbiased. And we can say else print coin is biased. All right, so that's a simple thing. That's nothing. Now what we want to do is we want to simulate the flipping of a coin.
Sir,
Now let's say I want to flip the coin once and return the outcome. How can I do this?
excuse me, sir.
Yeah.
Sir, in the if condition, whether it is we should have double equal to.
Yeah. Thank you. Now, so now I want to flip the coin once and get the outcome. How can I do this?
Sir, get the given the n, we can do it n times we have for loop.
Now, let's say I just want to flip it once.
Coin dot
Coin
flip,
dot
sir.
flip. Okay. So what I can say is outcome is equal to coin dot flip. What are the arguments I need to pass?
No argument.
No arguments. Okay. So this is one coin flipping. Now I need to flip it n times. So what I can say is for I in range of n, okay, outcome is equal to coin dot flip off. Now I need to add the outcomes, okay, to my list. Okay. So what I can say is, okay, out list, outcome list is equal to an empty one here, and I can say out list dot append of outcome. Okay. So what is the last step?
Return.
Excellent. So now I have to get outside the loop. I have to finish the loop. So D indent, and I say return output. Okay. All right. So this will simulate the coin flip. So you see this statement here will exactly simulate the coin flip. One coin flip. It's a random flip. Okay. So so that's the beauty of this. So this is really like flipping a coin with a given bias. Okay. So now we are saying this outcome basically will flip the coin once. So we are doing it for every iteration in the loop, and we're doing it n times, and we're appending the outcomes to out list, and we're returning the out list. All right. All right. Is this fine with everyone? Yeah.
In the range, if given the range as n, it will say the value is 100. Only it will consider up to 99 bytes. Sir.
Yeah. Yeah.
Then it must be n plus 1.
No. It goes from 0 to 99.
Okay. Sir,
Yeah.
also,
Yeah.
what bias here, sir?
Sorry?
Where do we pass? Given if the user gives the bias as 0.1,
Yeah.
where do we
Yeah.
pass the bias?
It's there in the initialization and the object construction itself. The bias is passed here. Coin of bias. That's the only parameter for the constructor.
Okay, sir. Okay, got it, sir. Got it.
Okay. So again, here also we can specify the bias is not necessary. So we can give it as a named argument to be consistent. And we can give the n as the first variable because the positional argument should come first, and then we can give the named argument bias. All right. So now let's first save this. Let's call this as coin tossing simulation. All right. So coin tossing simulation. So we have made this as general as possible. We have given in the user a option to specify the bias, and the number of trials can also be specified. All right. All right. So now what I will do is I'm running this. So there's an invalid syntax somewhere. I don't know why. Let's do this again. Oops. Why is there an invalid syntax?
whether the inequality def space in it.
Oh yeah, def. Sorry. You see, yeah, I'm getting old. All right, so it's definite, isn't it? It's a method which is essentially a function, but a function for a class. It's definite. You're right. All right, so yeah, flip as well. Good observation. Right, so now here we are. It's just running. We have only like defined a function and defined a class, so it's running without any error. So that's fine. Okay. So now we can basically interact with the user. So let's say let's say the user will ask the user. So bias. Let's say. So let's say. Okay. Bias is equal to input bias of the coin. Trials is equal to input number of trials. Okay. Print coin flipping experiment. Okay. So bias is equal to input bias of the coin, and trials is equal to this. Now we need to call our function. The function is coin simulation of trials, comma bias. Okay. Now the trials has to be a int, so we do a int of this, and the bias has to be a float. You see, we are not letting the user skip the bias. We are forcing the user to enter a bias. So that is a small thing you can address later. Okay, we have to use the yes or no and then address that. But that is fine. This coin simulation will return the out list. So we need to assign this to some variable, let's say result. Okay, and then we'll finally say print result. In fact, the result will be a list, and therefore what we can do is we can join the list as a string. Okay, and it will be a nice sequence that we get. Okay, so let's do both the printing. This is similar to the trick we used yesterday. All right, so now let's run this. So bias of the coin, let's just say 0.5 now. So now realize that the bias of the coin specifies the probability of getting heads. Okay, so that should be kept in mind. Okay, so is it head or tail that we are specifying? It is heads. All right, so that's how it's also coded. Number of trials, let's say 1,000. So line 33, there is some error. What is the line 33? So let's go to format or edit, show line numbers, options, show lines. So line 33 is saying list font. Okay. Let's just first see what is the outcome for this, and then we will do this. Alright, so bias is 0.5 and trials is 1,000. So now you see, we are getting the outcomes T, T, H, H, all this. Now you see each of this within it is a list. So that is the problem here. So how do we get out of that? So what we can do is we can say of 0. And when you say of 0, okay, You'll see what happens. Let's see print outcome. Okay, 0.5. Trials is just 100. The coin is unbiased. One flip, it just gives a key. So now it is proper. So now I can do a join, and this join will work. I'll get a nice sequence now. So let's just see this. So the bias of the coin is 0.5. I want to do 100 trials. Coin is unbiased. This is the sequence I get, and this is the real run. This is the run of heads and tails in a very compact form. Initially, I'm getting a run of 5 T's, then 2H, then 2T, 1H, and I'm getting a huge run of heads. So you see, it is possible to get a run of heads, and like this, you can analyze the statistics we are getting. Okay, what is the probability of getting a run of 4 heads? Okay, so all these things you can calculate. You can do the simulation many times. Put another loop, and then again get all these outputs and then look at them, isn't it? So what I will do is, let me just escape this, and we can also escape this. These were all debugging tools. So now what I will do is, let's run this again. So the bias is, let's say 0.8. I won't have more heads. Number of trials, 100. Now it says coin is biased. Now you see it's just a lot of heads. It's a lot of heads. And in the end, you have almost all heads because that is the bias of the coin. Okay. Now let's do this again. Let's flip the bias. Let's say it's 0.2. Okay. Number of trials is 100. So now I get a lot of T's. Okay. All right. So this is very sweet. So what we can do is, all right. So all right. So what we can do is we can run many experiments like this. How do I run many experiments like this? What I do is, let's say I want to run 100 such experiments. So then I say for I in, for experiment in range of 100. Okay. So this is the result. I'll say results is equal to a empty one. Okay. And what I will do is, so I will say this particular thing, I say results dot append of this, what I had here. Okay. So in the end, I have print of results. So I'll have 100 such experiments. Or let's say I just want 10 such experiments. I just want to demonstrate this. Okay. So now let's see what happens. All right, there's an unmatched thing here. So bias of the coin, let's say, is now 0.8. Let's say the number of trials is 100. So now you see what happens. So you see, so I'm getting 100 such, 10 such runs. Okay. So now I have 10 such simulations, and now I can analyze the statistics from these 10 such simulations. I have a lot of data. Lot of data that has been randomly generated. By randomness, I mean like according to the given formulae. Okay. And so using this, these are all empirical data. I can do a lot of analysis. So the coin is biased. I'm getting 10 times. So I don't need that. So I can, okay. Oh, it goes here, is it? So basically, I don't need this here. We can just say it here. And we can say if the bias. All right. All right. So, okay. All right. All right. So, so we are done with our program. We have, sort of very gradually built up our program. So the coin is biased, number of trials is 100, and 10 plates it, and mostly it will be a T because the bias is 0.1. It's very clear. So like this, you can play with this. Okay. So you see how we have built up the program. First, we wrote a class. Then we wrote a function for the simulation. We first defined a coin object. Then we wrote a function for the simulation. And then we wrote a script that calls this function and uses the coin object. Okay. And produces some very interesting results. That's something very interesting. Okay, so this is the entire exercise, isn't it? Okay, so now we have successfully been able to simulate the random flipping of a coin any number of times for a given experiment and simulate any number of such experiments all within one script. So now you have some results, you can analyze the results even. Okay, so is everyone okay with that?
Yes, sir.
Any doubts, anyone? Okay, okay. Okay. Yeah, any doubts, anyone?
No, sir.
All right. So, I want everyone to review what we have done today. I'll post all the materials. We have done something very interesting. Okay, starting from the basics, and we've used the random library as well, and really simulated the coin flipping experiment for a biased coin even. Okay, and usually these are the sort of experiments that will be done, and then you can analyze the results and produce some very interesting analysis as well. The coin flipping has led to a lot of results in mathematics. What is the probability that you get a run of 5 heads? Okay, and like this, and so on and so forth. There are many questions that can be posed. Okay, so all these questions you can study now that we have entire script to do everything for us. All right, so that is the power of combining the computation, isn't it? Computational thinking and computation using Python. Okay, all right. So any doubts, do post on the classroom. Okay, and any feedback on the session, I would welcome that as well. So tomorrow we'll continue with some more exploration of all these packages. Okay. So thank you, everyone. Bye.
Bye, sir.
Thank you, sir.
Right. Bye, everyone.